Hello everyone. In the previous part of the lecture, we had been discussing about the concept of contraction, and near the end of the lecture, I had briefly mentioned how this particular instance of contraction between a second order tensor and a vector can be represented in a shortened matrix representation in this form, furthermore in compact notation in this form. And the alternative contraction in this particular form of the index notation, the equivalent matrix representation was this involving the transpose, and it was here written in compact notation. So that was discussed in very brief, and I had mentioned in passing that there would be so I would be discussing a systematic way of obtaining these equivalent representations, and in this part of the lecture we are going to do that. Now before we can actually launch into that systematic way, we have to first go through a very short fundamental discussion about the outer product or the dyadic product of two unit vectors. So what we'll do is we'll consider first of all this unit vector e1 hat with this. Okay, so maybe it's better if I choose to do it with itself. So E1 dyadic product with E1 itself. Now as we had seen earlier, this dyadic product in equivalent matrix representation, it would be E1 hat multiplied with E1 hat transpose. Okay, now what that would mean is, so you note the matrix representation of the E1 hat is nothing but, in the matrix form, this is nothing but 1 0 0. Similarly, this one will be 1 0 0 but written as a row. So let me just quickly tell you what is going on here. So you see, suppose we are back in our very familiar XYZ coordinate system. So in that XYZ coordinate system, our unit vectors are I hat, j hat and k hat. Okay, now if you want to represent, so let me just quickly write this down in the rough column here. So suppose we are writing this I hat. Okay, so if I want to write the components of this I hat that are present along the different coordinate axes, what are the values? So along the x-axis, that is along the direction of I hat, it is 1. Okay, along the direction of j hat, it is 0, and along the direction of k hat, it is 0. So that is what is represented here by the 1 0 0. Similarly, if I had the j hat, that is the unit vector along the j direction, along the y direction, the scalar components of that unit vector would be 0 along the x direction, 1 along the y direction, because the entire unit vector is lying along the y direction, and along the k direction it would be 0, and similarly for k hat it would be 0 0 1, and exactly the same thing is going on here. So for the unit vector along the x1 direction, I have 1 0 0, and here also for the E1 I have the 1 0 0, but this transpose is making it like a row. Okay, so if I actually carry out the matrix multiplication, what I will obtain here is simply 1 0 0. It will be 0 0 0 and 0 0 0. So you see how this has shaped up. Only the element sitting in the first row and the first column, that has the 1 value. Similarly, if you consider the E1 dyadic product with E2, then what is it going to be? we have to write it like, so the equivalent matrix representation is E1 hat multiplied with E2 hat, but that comes with a transpose, and that is equal to, as before, 1 0 0, but now we have 0 1 0. So if we actually carry out this matrix multiplication, what we will obtain is 0 1 0 0 0 0 0 0 0. That's it. Okay, and you can actually quickly see what is going on here. So when you have the 1 and the 1 present, ultimately what is happening is that in the first row and the first column only the 1 value is appearing. Similarly, when you have the 1 and the 2 here, so it is like the first row and the second column, that is where the 1 is going to appear. The first row and the second column, that is where the 1 is going to appear. Similarly, if you had taken E2 dyadic product with 1, then the 1 would have appeared here. Okay, similarly for other combinations. So you remember this. Now, using these kinds of dyadic products between the unit vectors, we will be able to write the tensors of various orders in a more explicit fashion in the component wise notation. So what we want to do here is we quickly go back and look at the component wise notation that we had written for the vector here. So we want to write something similar for tensors of higher order. So what we are going to do here is for a tensor of order 2, we are going to write this as Eij Ei dyadic product with Ej. Now, what this Ei dyadic product with Ej means is that if you expand this out with the various combinations of I and j, and then you appropriately you take this put this I and j here also. So what I mean to say is that if you actually expand it out like this, that I equal to 1, j equal to 1, so that you have this thing plus E12, E1, E2 plus E13, E1 dyadic product with E3, and so on and so forth, all the 9 possible combinations until you end up with E2, E3 dyadic product with E2 plus E3 dyadic product E3 dyadic product with E3. So if you when you write down all these 9 things and you expand all of these things in matrix representation, ultimately what you are going to arrive at is the equivalent matrix representation of the second order tensor in this particular form. That is what I mean. Now let me just complete this thing. So this is the equivalent matrix representation obtained in a systematic fashion by expanding out like this. Okay, so how can we use this? So that is the question that we want to answer, is that how can we use this kind of an explicit component wise notation to obtain a systematic procedure to write out these kinds of things in terms of the index notation that we have done, instead of going through all this steps in between. So let's take up the case of the second order tensor T dotted with the first order tensor V. Now, in component notation, what this will be is Tij, Ei, diadic product with Ej, this entire thing dotted with Vk, Ek hat. Okay. Now, as I had mentioned in one of the previous parts of the lecture, that here this Tij by itself and this Vk by itself, they are like the scalar components by themselves. Okay. And all the strength of the vector or the tensor notations, they are carried by these various operations between the unit vectors. So we can take this Tij Vk to one side and write out the unit vectors sequentially like this as they appear. Okay, we just write them out in sequence. Now, among these things that are present, you identify that this Ej dotted with Ek, that is nothing but the Kronecker delta Jk. Okay, so this is Vk. The Ei remains as it is, but the Ej dotted with K, that becomes delta Jk. Now, some of you may be wondering that what happened to this diadic product. Well, you see, this diadic product is basically to explicitly denote that the fact that we are having this particular combination as a if you just look at this thing, this is like a like a second order tensor, the Ei and the Ej, but there is nothing really sacrosanct about or I should say that writing it in this diadic product form here and this dot product form, it should not give you the impression that this is perhaps more important than this. Okay, so so we should not fall under any sort of wrong impression in that way. So what is basically happening here is that there is very much a contraction going on here. So this Ej dot K, but in terms of the symbolic notation, that gives us this delta Jk, and the actual contraction business, that is achieved finally by the substitution of this Kronecker delta, whatever is common here. So again, we have two choices. This J can be this J here, the Tij, this J here can be replaced by K, or you can consider this delta Jk with the Vk, so that this K gets replaced by the J. So overall, what we can have is either Tik, Vk and the Ei present, or we can have Tij, Vj with the Ei very much present. Okay, so please do not get confused by the presence of this dyadic product. Okay, now if you look back at the previous parts of the lecture, you will see that whatever we have written here for this T dot V, here you see the T dot V, this was the Tik Vk, and we had to go through this long drawn procedure to obtain the equivalence between this index notation and this compact notation. And here, through the operations between the unit vectors, we have managed to obtain that without going through that long drawn matrix representation, and to see that ultimately whatever you are obtaining here, the explicit presence of one unit vector represents that this entity itself is a vector quantity or a tensor of order 1, so which is as it should be, as we have already seen. Now next, suppose we consider the T transpose dotted with V. So we want to explore what happens uh, to this alternative form. Okay, so let's go to the next page and consider that. So what we have is, so in the previous slide we had T dot V. Now we are going to consider the second order tensor T, the transpose of that dotted with V. So basically the contraction going on here. Now here in the previous page, you note that the T without the transpose, it was Tij Ei Diadic product with J. But when we have the transpose, we can still write it like Tij, but the fact that we are carrying out the transpose means that this particular thing has to be reversed. So instead of the Ei diadic product with J, we have to write this as the Ej diadic product with I. And if you go back a few pages, we have already discussed this particular thing here. So you see that this B diadic product with A, that was actually the A diadic product with B transpose. Okay, so that is the fact that we are going to use right now. Okay, so the Tij remains as it is, and the transpose, the fact that we are writing the transpose is implemented in this fashion by reversing the orders of the order in which the unit vectors are written, and this entire thing is dotted with the Vk with the Ek hat. Now as before, we take first of all the Tij Vk to one side, write out. So once you have the first line ready, the rest of it is following in a very algorithmic fashion. So this is dotted with K. We don't worry about the presence of this diadic product symbol and realize that Ei dotted with K is nothing but the delta Ik. So this is Tij Vk, Ej remains as it is, and this is delta Ik. And now as before, we are going to utilize the substitution power of the Kronecker delta, alternatively first with this one and then with this one to get equivalent expressions. So if you consider the Tij with the delta Ik, what we'll have is Tkj Vk Ej hat, or equivalently what we'll have is Tij. If you're going to consider this Kronecker delta with this Vk, then we'll have Tij Vi, and this Ej is present. And you note that in this particular representation, because the J is the free index here, so you have the presence of this explicit unit vector with the Ej, and here also it is the J which is the free here, and which is consistently present here with the Ej hat. Okay, and if you just quickly look back what we had obtained earlier, so this Tkj Vk or the Tij Vi, that is equivalent to this T transpose dotted with V. Okay, so everything is nice and consistent. Now the question comes, we have been doing various manipulations with the second order tensor and a vector. What about we consider two second order tensors? Okay, so suppose we have this particular combination. So A contracted with B. So no problem, we can write it like Aij Ei diadic product J, this entire thing dotted with B KL, so completely different indices used for the B, Ek diadic product L. So when we are writing this in this kind of an explicit fashion, we just take care that each of the individual tensors are written with completely separate indices. Okay, so here also we did the same thing. For the t we used I and j, for v we used the k, and then whatever had to take place took place in a very algorithmic fashion. And our belief is that the same kind of nice algorithmic simplifications will take place here also. Okay, so here you see we have first of all aij and the bkl coming to one side. Then we have these kinds of things present here. Now you see that the real operation, the real contraction operation is through the presence of this particular combination here, the ej dotted with k, and that result we know is the Kronecker delta with the jk. So we'll write that here, delta jk, and whatever is remaining here we'll just write it like this. Okay, now you see the way that this term is written here, there is absolutely no problem. Okay, because whenever we are not writing anything in between two entities like that, it basically by default means that there is a dyadic product. Okay, but if you really want to make it very very explicit, you can put the dyadic product symbol here. Okay, there is no problem. Okay, and you will see that at the end it will come out as very consistent. Okay, so what we can do here, so just like before, we can consider the Kronecker delta with this term, in which case this j will become a k, or equivalently what we can do is we can consider the Kronecker delta with this one, in which case the k will become this j. So first of all we do this thing, ai k b kl ei dyadic product with el, or equivalently we have aij b, so this k gets replaced by the j, so this is bj l ei dyadic product with l. And you see in this term, or in this term, both of them being equivalent, what we have is that this I and this L, they are the free indices. So had we written this in a pure index notation, then this I and this L being the free indices would have indicated by themselves that this particular entity is a second order tensor, and this k is just a repeated or a dummy index. It does not contribute to the order of the tensor. And very consistently in this particular component wise notation, we see that the presence of this ei dyadic product with L represents that this is indeed a tensor of order 2. Similarly, in this case, the j here is the repeated index. It does not contribute to the order of the tensor. The free index I and the free index L, they are contributing to the tensor of order 2, and that is very much consistent with the presence of the I and the presence of the L here. Okay, so now you see a second order tensor A dotted with another second order tensor, or contracted with another second order tensor, it is giving us a tensor of order 2. Now here there is a single dot present, which explicitly means that this is what we have here is a single contraction. As opposed to this, we could also have a double contraction. Double contraction means, so here ultimately what is happening is that, so this was initially aij and this was bkl. What we are basically doing is that we are setting the j equal to k. You see, whatever is happening here, this j is becoming equal to k. So ultimately we end up with aik bkl or aij bjl. Okay, so ultimately the heart of the matter is that we are setting j is equal to k. Now had this been a double contraction, then another index also would have been set equal. Okay, so in that case the I would have been set equal to L, and you would have ended up with a tensor of order 0. Okay, so I think in one of your problems in the problem sheet of this chapter, you have a problem like this. Okay, now alternatively, suppose we want to find out what is the result of A transpose dotted with B or contracted with B. We can quickly do that as an just to have our ideas clear. So A transpose B contracted with B. So just like before, we will write the Aij just like that, but because we have the transpose here, we'll write the Ej dyadic product with Ei instead of the Ei dyadic product with J, and this entire thing will be dotted with the BKL Ek hat dyadic product with El. So now, as we have always done, so Aij BKL will come to one side. We'll write all these unit vectors in sequence as they appear. It's a very algorithmic system, so it's very easy to deduce the final expressions in this form. So we have Aij BKL and this Ei dotted with K, that is going to give us a delta Ik, and whatever we have remaining we can just write it like that, Ej and the El, and just to make things very clear we'll put this dyadic product here. So finally what we'll have is, either by considering this delta Ik with the Aij, in which case we'll have Aj B Al Ej hat dyadic product with El, or we can take the Kronecker delta, we can consider the Kronecker delta with this BKL, in which case we'll have Aij B, and in this case you note that the K gets replaced by the I, so we have the BIL. And finally this thing. And just as before, you first of all note that the free indices present here, the J and L, they appear in this unit vectors, the Ej and the El. Here also the J and L are appearing here, the JL and L are appearing here, and the positions of the dummy indices in the first position, here in the first position with the second one, here also the repeated index or the dummy index are present in this first positions. Okay, so when you have A transpose B, you end up with AKJ BKL or Aij BIL, as opposed to the previous case when we did not have any transpose, you ended up with Aik BKL or Aij BJL. So without the use of this systematic notation, it sometimes becomes very confusing to write the equivalent index notations from this compact notation. So there can be two other combinations where you have A dotted with B transpose, and then you can also have A transpose dotted with B transpose, but I'm not going to go through all those things. You can try them out on your own. All right. I think I'll close this part of the discussion here, and in the next part of the lecture we are going to continue with another topic within the chapter of mathematical preliminaries, and that is going to be really useful to us as far as the understanding of the tensors is concerned. All right, thank you very much.